A lot has happened in AI over the past few years. You've probably heard terms like prompt engineering, tokens, context windows, embeddings, RAG, vector databases, LangChain, LangGraph, MCP, agents, Claude, Gemini, and more. If all of that has felt confusing, this video is for you. In this video, we'll assume you know absolutely nothing. We'll explain these concepts through one practical project so that by the end, you'll have a clear big picture understanding of how modern AI systems work. We'll start with LM fundamentals, then move into embeddings, vector databases, RAG, LangChain, LangGraph, MCP, and prompt engineering. Let's begin with the basics. When you ask an AI chatbot a question, the response usually comes from a large language model, or LM. These models became widely popular after ChatGPT exploded in late 2022. LLMs are trained on massive amounts of text from books, websites, code, research, and many other sources. Their job is simple in principle: predict the next most likely piece of text. That sounds basic, but at scale it becomes powerful. Models like GPT, Claude, and Gemini can write, summarize, explain, and reason across many subjects, but they also have limitations. For example, if your company has 500 gigabytes of private internal documents, that data was not part of the model's training. The model doesn't automatically know your policies, procedures, or customer records. So how do we give it that information? The first concept to understand is the context window. Think of it as the model's short-term memory. It includes the instructions you give it, the conversation history, and any extra documents you attach to the request. This context is measured in tokens, which are small pieces of text. In English, a token is often about 3/4 of a word. The problem is that context windows are limited. Even very large models can only look at a certain amount of text at once. So if your company has hundreds of gigabytes of data, you can't just paste everything into the prompt. The model can only see a tiny fraction at any given time. That's where embeddings come in. Embeddings are numerical representations of meaning. Instead of storing text only as words, we convert it into vectors, which are lists of numbers. These numbers capture semantic similarity. For example, vacation policy and time-off guidelines use different words, but they mean similar things. Their embeddings end up close together in vector space. This is useful because people rarely search using the exact words from a document. Someone might ask, "Can I wear jeans to work?" while the official document says dress code policy. Embeddings help connect those meanings. Once we have embeddings, we need somewhere to store and search them. That's the role of a vector database. A vector database stores embeddings and lets us search by meaning instead of exact keywords. Unlike a traditional SQL search, which depends on matching words precisely, a vector database compares the user's query embedding to document embeddings and finds the closest matches semantically. Before storing documents, we usually split them into smaller chunks. This is called chunking. It makes retrieval more accurate because smaller pieces are easier to match. Often chunks overlap a little so that important context isn't lost at the boundaries. Now we can understand RAG, which stands for Retrieval Augmented Generation. RAG works in 3 steps. First, retrieval. The system converts the user's question into an embedding and searches the vector database for the most relevant chunks. Second, augmentation. Those retrieved chunks are inserted into the prompt as extra context. Third, generation. The LLM reads that context and produces an answer grounded in the retrieved information. This is what makes private AI assistants so useful. Instead of relying only on what the model learned during training, RAG lets it answer using your company's real documents at runtime. Now, building all this from scratch can get messy. You need model access, prompt handling, memory, retrieval, tool use, and flexibility to switch providers. That's where LangChain helps. LangChain is a framework that provides reusable components for AI applications. It helps you connect models, prompts, memory, vector databases, and external tools without writing everything from the ground up. It acts like an abstraction layer that speeds up development. But sometimes you need more than a simple chain. Real business workflows often involve multiple steps, decisions, and loops. That's where LangGraph comes in. LangGraph lets you build stateful workflows using nodes and edges. Each node performs a task, and each edge controls where the process goes next. This makes it possible to create more advanced agents that can reason through multi-step tasks instead of just responding once. And that brings us to agents. A plain LLM generates text. An agent is a system built around the model that can use memory, tools, and workflows to decide how to complete a task. It can retrieve documents, call APIs, check databases, and then generate a final answer. To make these agents even more powerful, they often need to connect to external systems. That's where MECP, or Model Context Protocol, comes in. MECP is a standard way for AI systems to connect to tools, APIs, and databases through self-describing interfaces. It makes integrations more reusable and easier for agents to work with. Finally, prompt engineering is the skill of giving better instructions. The clearer the prompt, the better the result. Good prompts define the role, task, format, and constraints. Techniques like zero-shot, one-shot, few-shot, and chain of thought help guide the model depending on what you need. So when you put it all together, the picture becomes clear. LLMs generate language. Context windows hold working memory. Embeddings represent meaning. Vector databases search that meaning. RAG brings in the right knowledge. LangChain helps build the application. LangGraph handles more advanced workflows. MECP connects tools. And prompt engineering improves output. That's modern AI in one system.